Klein. Okay. Okay, das sieht auch schon besser aus.
So, was war das Problem?
Es ist immer, wenn der mal in Standby geht, dann hat er Problem, also es liegt an meinem Rechner. Das liegt nicht. Okay. Sensitiert. Okay, so let's start. Yeah, everything's ready. So,
perfect.
Yeah. So, like, just ask any question anytime you want to ask a question. Like, I'll try to answer that. So,
Okay.
like, objective now of what we're doing now is like to fit thread sensitized emission together with of the acceptor. Excited by thread, and like of the donor de-excited by thread to the acceptor, together with the direct excited acceptor and the direct excited donor. So what you need for this analysis is, first of all, for the donor data, like here in this folder I have the donor data, that's the donor in the absence of an acceptor, excited by the donor laser and emitted in the donor channel, the donor directly excited, and then the emission of the donor in the acceptor channel for the determination of the crosstalk. Then the thread sample, so this is here DA, designates the thread sample. The thread sample that is excited by a donor laser and that is emitted in the donor channel. And then also, like, this is only in principle for the crosstalk. These two should give the same for the crosstalk. This is the donor excited thread sample with the emission acceptor channel. This is the thread sensitized emission that, together with like the donor only sample, will be analyzed later on. So moreover, to analyze the thread sensitized emission, we need the donor only, the thread sample that is excited by the acceptor laser, and then we detect the emission in the acceptor channel. So the easiest now is like if we start with the donor only. So first of all, to analyze the data, we need the instrument response function of the donor channel. And you can load the data just by clicking on this file and dragging it here to this data set, lower data set window. First of all, like, you have to check what file format that is. Here, if I open the file, this is Klaus Seidel lab specific file format where like parallel and perpendicular detection channel are just saved subsequently in the file without a additional column which specifies the time. So like this is in principle, like here, what is here shown is just a count that is detected in the histogram. So therefore we need, in addition to this file, which is a polarization resolved file, we have to know the time resolution. In this case, the time resolution is 32 picoseconds. So to load the file, first of all, you have to specify here by clicking on this checkbox. You can specify the time resolution. And then we need a repetition rate that is
40 megahertz.
40 megahertz. And as this is a Geordie file format, so meaning there's a parallel and perpendicular detection channel, here you have to click on this VV/VH Geordie file format. So now we're going to do kind of like...
one more question regarding the G factor here. So should I type it there or not?
Yeah, exactly. This was I was talking about it now. Like, it's like you have three options in principle when you load in these Geordie files: VV, VH, or VM. And VM is actually not vertical magic angle detection. VM here is just VV plus 2 times GVH.
Okay, so it's
like this. Okay. This number here is then the G factor. I think it should show here. No, it doesn't show. Like, this is the G factor here.
Okay, yeah, it should be 0.98.
0.98, so it's close to, probably wouldn't make a difference.
Yeah, it is.
Okay, so now you can simply click on the file and drop it here to the loaded file window. Now, do exactly the same for the donor sample, donor excitation, donor emission. This sample here, the donor-only sample, donor excitation, acceptor emission, we don't need to load here. We have to only analyze how much counts we have in the channels. Like, I will talk about this later. So for the donor-only samples, we approximate it simply by sum of exponentials. So like here, by clicking on these different files, it's a bit short, doesn't fit. The second one is donor-only, just remember. You can then here, once you click here, for a specific file, you load it into the program, you can select different models. So like there's a lifetime model, that's just the sum of exponentials, Fred model with discrete Fred rate constants, Gaussian distributed distances for Fred, or like this PDDEM, which is a model for the energy migration between a donor and acceptor and back. So like for homo-Fred in principle, or like here one chain model. So for donor only, we first use like the lifetime.
Noch 5 Minuten, okay? Okay. Muss alles noch ausmachen.
Okay, here, so you click here on the data, you select the model, you click on add fit, and then on your window here to the right, like you get displayed the data. So here to the left, there are multiple panes, kind of like where you can click. Like here on this loading window, you can also click here to the top and move it somewhere else in principle. On the loading window, you can load the data. In an analysis window, you can, for a selected model, so meaning for a selected window, you get displayed all the options that there are. And on this plot window, you can change kind of like the way that the plot is displayed.
Okay.
I mean, like, yeah. So on the analysis window, you see here now only the decay and then the model superimposed. The decay in this case is shown in orange. And here to the top left, this is are the weighted residuals. To the top right, like this autocorrelation function of the weighted residuals. And here, with the right mouse button, you can zoom in and out. And with the middle mouse button, you can move the plot. When you click the middle mouse button, you can move it. You can see then the fit range. This is the number of the data point and the chi-square of the corresponding fit. And this dV is another quality measure, so that should go up. So like as chi-square is just the sum of the square, the sum of the weighted squares, and the dV is like another fitting parameter that is a quality parameter. So here,
correlation or
it is autocorrelation based. Yes.
Okay, perfect. Okay.
Okay. Here on the top, you have to next of all, you have to load the response function. So like here, you see like the data is not convolved because like the program doesn't know what is the response function. Okay. Here on the top, you can in principle like also group data sets, and then you can select a different data set. Here, we only have one data set in the group, so like we only have one data set that we can select. And here, like as I said, like next step is in principle like the load to response function. This you can do by clicking on the 3 dots here. Then you get displayed another window where you have all the data sets that are loaded, and then you select your response function. So now the response function of the instrument is shown here in blue. And now I'll go through all these parameters that are relevant here for the model.
Okay, but I think in this, just quickly, right?
Yes, just very quickly. So here LB, like this is the background of the response function. So like if I read here, you can see it's roughly 10. So let's put here 30 as the starting parameter. TS is the time shift. So you see if I put 10, the response function shifts. Let's start with 0. SC is just the prefactor of the instrument response function. So if I put here 0. And then it's added to the model. So like if I put here 0.5, you see then the response function. BG is the background, so here it's the constant background. And then here are the lifetimes. So here it's just one. This is the amplitude, this is the lifetime. If you click here on add, you can add more lifetimes. Here, this is not relevant for this data set because we treated it as just as a magic angle data set. This is for rotation. So like I recommend you that here either you fix these parameters or you just delete the rotation, because like then you have less parameters in the model.
Okay.
The next is for corrections. Like if you have a good instrument, you don't need it in principle like this to linearize your model. I mean like to disturb your model so that it fits a nonlinear data set.
Mm-hmm.
So like now here on the top right, here on this button, you can click to estimate errors. Like then it will do a Monte Carlo sample, Monte Carlo sampling run and estimate the errors of the 3 parameters. I didn't mention that like the first is kind of like the fixed parameter. The middle, if you click once here in the middle, then all the parameters within a group are linked together. And to the very right, you can set a range that is allowed for the parameter. So now let's just fit maybe. Okay. Here and to the right, you see the fit result of 1.78 as the chi-square. Not very good, so maybe we just add another lifetime and then now we have a perfect fit. See here, like this chi-square goes down and this fitting parameter goes up. This quality parameter goes up. So this is now already, I would say, perfect fit.
Mm-hmm.
So let's move on. And then the next step is that we look at the donor alone. I recommend you doing like this fits also for like this thread sensitized emission iteratively, meaning like you start first with the donor, then you look at the thread sample, then you make your acceptor, then the thread sensitized emission, so that you always kind of like iteratively try to optimize your model against your data. If you try to do everything at once, like you very likely fail in the optimization. Mm-hmm. So next is you just load the donor-only sample and the thread sample, donor excitation, donor emission. So if you just click on a data set, drop it here, it's in the list. And now like the model you likely want to use for that is here Gaussian model. So thread Gaussian means like Gaussian distributed distances. You click on add fit. And you have your data set here.
Mm-hmm.
Okay, here again, we have to do the same. We have to place it here. We have to set a response function. It's again the same response function. Some starting value for the background of the response function. I delete rotational times. I just keep one donor-only distances. And now here, what you can do if you know that the count rate is very similar, like this is kind of like the first step when you build a global model, is you can connect the time shift. You could connect the time shift. This TS is for time shift of the response function to the time shift of the donor-only sample. Then if you describe both data sets together, you have one less free parameter. To link parameters, here you have like this middle checkbox. If you click on the middle to the right, like with the right mouse button, then you see displayed the different parameters that you have, and then you want to go here to convolution and set TS for time shift, and then you fix the time shift to the value you have in this model. Okay, now to analyze the donor in the presence of thread, we have to know the donor in the absence of thread. So we have to connect these parameters to the parameters we have here. There are multiple ways, like I'll just show, I think I'll just show both because that's maybe best. So like, first of all, like then what you can do is like that you mimic the model so that you have also 2 lifetimes here. So I added 2, these are the lifetimes of the donor in the absence of thread for this particular sample. And then as for the time shift, you can right click and then specify the connect the fractions, and connect the lifetimes. So now, like you see, like these values are grayed out. The reason is because like they're not part of this model anymore. Like they're described in the model of the other data set. If I now click on fit, you see here like now the fit result of that. It tells me 56 angstrom. Yeah, and here one thing you also have to know is like here, like this is this first radius. This you have to know. You have to know the lifetime for this first radius, and of course kappa square. Okay, now one parameter that wasn't linked so far is like this background of the response function. You could also link this, then you have one less parameter. So I link it here to the background and then fit again, and then you see you get basically the same fit, just with less parameters. Okay, so now we have our two data sets and we want to make, they are now fitted individually. Maybe we want a global model for that. So like that we describe both data sets by one model. So a global model is nothing else like then another data set, but like this data set doesn't have its own data. It refers to the data of the other data sets. So look, to create a global model, you just go to load, global model, and then there is no model for global model except for global fit. Then you click on add fit. You get presented an empty new window. And if you go to analysis for this global fit, you can add new data sets. So here to the left, here on this next to the fit, if you click on update, you should be presented all the fits that are in the program so far. If you leave this checkbox in and just click on add, all fits will be added. So all the data sets of all the fits will be added to the global fit. You can also clear again. If you only want to add an individual one, you can uncheck here this box and then select an individual one and then add it individually. Okay, now we have these two data sets in a global fit. If I click now on fit, on the global fit, you'll see that here it just added, and you know what you're doing, that you added the fits, so the names of the fits with data sets that were optimized. And now, like these parameters that are shared among the data sets are optimized for like the joint data set.
Okay.
So this is the idea of a global fit. So, and you see here in a global fit, in principle, like in all fits, you have it like that there is a representation for the data, for information representation that collects all the parameters and the respective values. And here, this is for estimating errors. You get a residual plot, and I think in newer versions, you get also here displayed all the residuals of the individual fits. So here you see like a list then of the different fits that are part of the global fit with all their parameter names, with all the values. Okay, so now we have a global fit for the donor and the donor in the presence of threat. I said like there is another way of connecting lifetimes, because let's say if you have multiple lifetimes, this can be very tedious to do all this clicking. Okay, maybe I first remove this. And then another option is to link it directly or to read the data from the other fits. So like if you click on read or double click on read, then you can read the values of the lifetimes here. So of course now it's the same value, but like if I change it here, let's say to something strange, let's say 10. And then here, read in the data. You see here, this was changed. Okay, like this wasn't updated yet, but in principle, like this number here is also 10. Like it's just not updated. Like this is a bug in principle.
Okay, but so there's no cross anymore, right?
No, like you can use it to read from other data sets parameters. This reading button.
Okay, and then simply fix it. Okay.
And then simply fix it.
Okay.
Another option is you can delete those, and then you can say like, I want to, now you don't have any lifetime of the donor in the fit, but you could say I want to link it to the lifetimes of which I have here. And then like all the donor lifetimes are referred to these lifetimes which you have here.
Okay.
So if you click here on link, then you can say like, I want to link it to those lifetimes. It's again not updated. And then like it's linked without doing all this clicking. But once you link lifetimes, you cannot unlink them anymore.
Oh.
So like it's a one-time thing, and then yeah. But it's maybe more convenient. Okay, now the fit ran away. Okay. I would say like the most general is like still, I close now the data sets and we start over, just very fast. So that we, because like it's, if you find something that something strange is happening, better like just start over again. So at the donor, note the response function, 2 lifetimes, no rotation, fit, thread sample, donor in presence of threads, Gaussian model, note the response function, 2 lifetimes that I connect with these lifetimes, with these amplitudes and lifetimes. And the background I also connect to have less parameters. Time shift, I guess like the count rate is similar, so I can also connect this. This didn't work. Scatter.
Okay, the background is negative. Okay.
I think, yeah, like here I clicked wrong. I connected the time shift wrong. Okay, now it works.
Okay.
Do global fit. The global fit, here click a few times on update. And then like we know already that we want to add all of them. So, and then we can do global fit, and these two data sets are fitted together. So next thing is like we want to fit the acceptor only. So because we need an acceptor only to describe the flat sensitized emission. So for this, I need the response function of the acceptor only. Like this is the response function here of the acceptor only in this case. And I need the acceptor only. The acceptor only I get from the direct excitation of the donor only, thread sample. So acceptor only is again just as described by a set of fluorescence lifetimes. So like Jan Henrik, what was the G factor in the sample for acceptor only?
For acceptor only, I would also string it 0.98.
Okay, 1, roughly.
Yes.
Okay. Now we need a response function. Here you see, if you zoom in, some funny feature. This looks like maybe there was a time shift between parallel and perpendicular. I don't know. But it's interesting because it's not there in the instrument response function. Honestly, I don't know what it is in this data set. You mentioned that there might be crosstalk from the donor to the acceptor, or
there is surely, yes.
Okay. So it might be in principle like emission crosstalk from the donor to acceptor.
From the donor to the acceptor, there might be crosstalk of 50%, maybe.
How much?
50%.
50%.
50% or more, yes.
Oh, okay.
Thomas?
Yeah, like I'm just thinking how to analyze this. 50%.
Mm-hmm.
But this is acceptor only, so there shouldn't be anything. So, but is there excitation crosstalk from the acceptor? So does the acceptor laser excite the donor?
No.
Okay, so
But
like,
this, of course, there might be a little bit, I have to look it up.
yeah, maybe this is what we see here, that the acceptor laser excites the donor.
Yeah.
Or I don't know, like this is really strange, this bump here. I don't know what it is.
Let me see.
I would say for now, let's ignore it, like, and just cut it away. But like, this is not so nice.
Okay, so laser 2 is exciting our acceptor with 15%. Okay, and our red laser is exciting our Alexa, so our donor, with 2%. But the power is much higher. So.
Yeah, but like you said, like this wasn't a pi measurement, so
it's not a pi measurement.
yeah, it's like maybe you should check what this bump could be, because I don't know.
Yeah, I agree.
Okay, so like I just add, let's say for start to lifetimes, and see that it fits more or less. Here the beginning doesn't fit very well. The reason is like this bump. So like I don't know, like if there is just to try, I could add a third lifetime, but no, it doesn't improve. So here there's some, okay, just play a bit with the starting values. So no, it won't get much better. So like here, like this is like probably like this beginning could never be described by the response function. So you have to cut it away.
Okay.
But maybe just check what it is.
Yes.
Okay, so now we have the donor in the absence of thread and in the presence of thread. The acceptor direct in the thread sample directly excited by the red laser, so by the laser for the acceptor. Now we need the acceptor sensitized in thread sensitized acceptor emission. So in this case, this is here like the dx acceptor emission. No, here donor thread sample DA donor excitation acceptor emission. And what we moreover need is the response function of the red lasers to the green laser. Red detectors to the green laser. You know what I mean, Jan-Henrik?
No, I'm sorry.
Whoa. So we need another response function.
Okay. Okay.
We need a response function of the red detectors.
Yes.
When you excite with the green laser.
Okay. Yes, this I can produce.
Because we are going to detect with the red detectors that are not the green detectors when we excite with the green laser.
Yes. Give me a second.
Maybe I stop the recording while you, or I just continue and then I cut it out or whatever. Doesn't matter.
Okay. So no. Okay, my program crashed. Sorry.
So now we need thread sensitive. We want to analyze the thread sensitized emission, meaning we have the thread sample, we excite the donor, and we look at the acceptor emission. So here, this is the response function of the acceptor for the donor laser. I'll just drop it here. And now we need, as I said, like for the thread sample, like acceptor emission. And here as a model for like this data set for the thread sensitized emission, you can select here like this partial donor-donor energy migration, which is the most general model you can have for thread in principle, but like you can just adjust the parameter such that is also for like the special case of thread sensitized emission also applicable. So just to explain what this PDDEM model is if you imagine that you have a donor, two fluorophores, one to the left, one to the right. Let's say this is our A fluorophore, this is our B fluorophore. In principle, like you could have energy migration from alpha to beta or from beta to alpha. And then you have emission here. So, and what we're looking at in thread, if we only look at a donor, we only look at these lifetimes here. If we look at a thread sensitized emission, we look on these lifetimes here. In a special case of hetero thread, we don't have the back migration. So like this K beta alpha like is 0. So we have only this case where we have a migration from the donor to acceptor. Therefore, like the thread sensitized emission is in principle only a special case of the donor-donor energy migration. And like this we are going to use now, like this model. So like this is what you have here in this PDDEM model. And here again, like you have to select, here you have a bunch of more parameters. First of all, you have to select your response function. In this case, like this is this erythrosine red. That's the response function. And now we have to specify the lifetimes of the fluorophore A and lifetimes of fluorophore B. Or meaning A and B, just like it's the same as alpha and beta here in this scheme. So A is our donor, B is our acceptor. And like to turn off like this back migration from acceptor to donor, there's one parameter that is here like this. You have two parameters here, like A to B and B to A. A to B is 1, B to A is 0. Like the amplitudes of the rate constants are just multiplied by this parameter, meaning that there's no back migration from the acceptor, which is B in this case, like to the donor.
Ah, okay. So it's actually just the rate. Okay. Hmm?
It's it just multiplies like all the amplitudes with
Yes.
like this number. So just for convenience, and then like of course like as all the amplitudes for like this, all these amplitudes here for like these rate constants are multiplied with 0, like you end up with this model again.
Okay.
But like this is in principle like the most general you can have, like you can do also homothread.
Okay.
Okay, now we have to specify all our lifetimes. We had 2 lifetimes for the donor, 2 lifetimes for the acceptor. I just again do it manually. It's maybe not the most efficient, but the most tested.
I think we skip quite a lot of parameters for the migration there. There's a pure.
Yes, like I'll talk about that later.
Okay, okay.
Once like this here is okay. So I specify something for a response function, background, maybe like this. I fix it just to have less parameters. And now we just talk about like all these parameters here in this PDDEM model.
Okay.
This is, as I said, like just something that is multiplied to all the prefactors of the. So like you imagine here in this distribution, you don't have distance distribution. In fact, what you have distribution of rate constants. Okay, like sometimes it shows. Here you have a distribution of rate constant. Like this looks a bit funny now because like, yeah, because like we have this Gaussian, which is Gaussian in the distance. We have now discrete lifetimes. So then of course like we get discrete lifetimes here, and we get positive and negative factors because of this PDDM model. Okay, so let's go back here to the.
Okay, but this would mean that if we use the spread sensitized model here, this PDDM fit, we don't end up with a distribution for.
No, you get a distribution. You optimize like a Gaussian distance distribution against your data, but internally, like this Gaussian distance distribution is represented by a set of fret rate constants that is converted with the lifetimes you have in your model to a set of lifetimes.
Okay, got it.
So like you have these distances are converted to fret rate constants, and then the fret rate constants are converted with the lifetimes you have to lifetimes that are optimized against the data. Okay, going back like to these parameters we have here, these are just these prefactors that are used to kind of set the direction in principle. Then here pure A and pure B. This is the amplitude of pure donor of pure flow for A or pure flow for B. Meaning, let's say if I set this to, can be any number in principle, but like say if I put it to 10, then you see here like it's okay, it disappears. If there, you set there a number, then you see that the decay changes. And then you have a larger fraction of acceptor only in principle.
Okay, but the question is how could you, I mean, now it's fixed, right? So pure B and pure A, it's fixed, but you say actually it's a fraction of donor only in the decay, or no, acceptor only?
No, it's a fraction of pure acceptor only, or pure donor only. No flat.
How would you like to determine this? I mean, these are fixed parameters. Shouldn't they be fitted?
Yeah, like they should be free. Later they should be free. Like now, like they're just fixed for the start.
Okay, I agree. Okay.
So because you don't know them, but pure A you can estimate from your donor only fit. From your donor only fit, you know that it's roughly 29. 29, yes. Pure A we don't know.
Okay. But it should be super low.
I don't know what you. I don't know.
The reason is actually that simply the donor strand is with biotin attached, so there's actually no, and the acceptor only is washed out afterwards.
Okay, so that meaning there should be less acceptor only, or
exactly.
In your particular case. Okay.
Exactly.
Okay, so like this is, I hope this is clear now, like this is donor only, acceptor only for this particular setting. And this is how strong the acceptor or the donor only of fluorophore A is excited by the laser. This is also just a prefactor. So meaning that, and this is how strong the acceptor fluorophore B is excited by the laser pulse.
Okay.
So here we would have 2% direct excitation compared to 98% excitation of the donor.
Okay, this would be my next question. So these values are now normalized. So these are percentage, right?
This is internally there's no normalization. You would have to calculate these values based on your spectra.
Okay,
and
based on the spectra.
Non-normalized, normalized values doesn't matter. But I would use normalized values, like just.
Okay, but in some they have to be 1, right?
They don't have to be 1.
Ah, okay, perfect. Okay, then
But I would normalize. I recommend you normalizing them, because personally I always work with normalized values, and I haven't tested whether something funky will happen if you put in a very big number.
Okay.
I don't know. So like I would just normalize it to 1.
Okay.
So, and here, as you have the excitation probabilities, you could say, or like excitation prefactors, you have the same for the emission. So this is now, because like flow 4b, we said like as the acceptor, the emission of flow 4b for like this particular setting is 98%, and flow 4a, which is the donor, is 2%. So what we have now is the acceptor channel. If I reverse it, oops, no, typo. If I reverse it and put here 0.8, you would have the donor channel. Because like we have now the emission of the donor and less emission of the acceptor. But we have, so like in these numbers, you can in principle also calculate based on your spectra. So like these excitation and emission probabilities, like they're 100% determined by your spectra. Okay. So I mean, like you have a rough estimate for like these numbers for your particular settings, or?
No, not really yet. I can.
Okay, but you said like it's your acceptor gets excited by 50% or by the donor laser.
Okay, so the acceptor is excited by the donor laser by 14%.
Okay, so we can put 14 here.
And the acceptor is excited by the pi laser, so by the red one, by roughly 2%.
Acceptor is excited, what?
No, the donor.
Okay, like this 2% is correct in principle? No.
Yes.
No, we don't look at the excitation of the donor by the red, but we don't have the red laser pulse here. We have only the blue laser pulse.
Okay. So again, what kind of value do you need? I mean, the excitation.
So like the emission, how much emission crosstalk? We need the excitation. You need all the crosstalk. So like the excitation probability of the donor, the excitation probability of the acceptor by the donor laser, the emission probability of the donor in the acceptor channel, and the emission probability of the acceptor in the acceptor channel.
Okay. I think I cannot calculate that fast now.
Okay, let's pretend we knew them. Like, let's pretend it would be those values, for sake of simplicity. So I guess like there is how much crosstalk from the donor to acceptor is there? 20% or
no, 50%.
50%.
Yeah, from donor to the acceptor, it should be minimum 50%.
Okay, then let's put 50% here as a crosstalk.
Okay.
Okay, now, like the lifetimes are all connected already. Scatter, I don't know, usually you have very little scatter in the acceptor channel if you excite by the donor. The reason is because like you don't have the laser light leaking to the detector usually. So like maybe we can start here as a beginning with 0. And the background, I would also estimate here, maybe it's 5, maybe 10, I don't know. Now here, this you can connect now again, like in the same manner to the distance of the donor, and this fraction we can in principle fix. So now if I click here on fit, you see it doesn't fit. Okay, now here like this pure A, I connect to the fraction of donor only. And pure B, this we don't know. We don't know how much acceptor only we have, so we don't know it. Again, it doesn't fit. Maybe we set it to 0. Just said like you wash it away. Okay, what we can try now here is if you go to global fit, update and add again, you see now all 4 fits in the global fit. If you fit now, it should fit everything against data, and yeah, this takes a while now, a few seconds.
So is there somewhere a button to see the process?
No.
Okay.
Okay, you see now like all the fits are bad, but all are bad equally. All are equally bad. Let's put it that way.
Okay.
So meaning that we did something wrong here with the values we had. So my guess is, so like therefore I said like it's maybe a good idea to do it iteratively. So you can do, if you want to, another global fit where you only fit, let's say, the donor only. I'll make it bigger here, where you only fit the donor only donor only fits. So this and the donor only, just to make sure that they are good. Then here I would fit this again, because this is the acceptor only. Because now what we're left with is kind of like that this fit does not work. And there are, as a start, I would just leave some parameters open. Namely the ones we know the least. So oops. It's crazy. This N0 is the amplitude. In principle, we don't need it.
What about the donor only fraction value for lifetime? This is wrong, I guess.
Donor only fraction value for, what do you mean?
By golden distances, the topic.
Ah, like this doesn't have, like it's just, it doesn't have a meaning, like it's just there.
Ah, okay.
It doesn't mean anything.
Okay, always, or?
No, in this particular case, it doesn't mean anything.
Okay, but
Because
usually
like this is all handled by like this features that are up here. So this doesn't mean anything. Like
okay.
So it seems like now we can, okay. Now we have to play a bit to find out what's going on. So let's say you have 100% acceptor excitation and only acceptor only. I am just playing with the parameters to see what's going on. So no donor excitation and no donor emission. So like this acceptor only decay, and you see it doesn't fit. So like meaning like this decay is slower, what you have here. And now let's look how the donor only looks like. I just put 1, 1 here and 0, 0 here. And this is the donor only with fret. And yeah, you could also not describe that with these numbers. So let's look now for the donor only, if it would be an only donor only. And like also like this, you could never describe this decay as it is. So meaning what we have here is very likely kind of like low fret, I would guess. So because like a low fret decay will kind of like look like a rise term, and then it looks like more like a bump in the data. This is how a low thread decay would look like. So that we cannot fit, maybe because like there is in fact some additional distance. I don't know. What do you expect, Jan Henrik?
For distance, so we this is actually a high thread, so the efficiency is 50%.
50%, okay.
So the first radius, if you want to type it directly, it's 70.
First radius is what?
70 angstrom.
Okay. For which lifetime?
A 3.9. So a 3.9 is the reference, right?
Okay, you get 76 angstroms, okay. And what do you expect?
70.
Okay. You get 76.
Yeah, there's always a small contribution. For the outer distance, I'll solve a smaller one, I would assume.
Okay, let's look at the parameters again. Pure A, donor only, 0.2. We can link it. And just check here what I got, 33. Just put it here and fix it first.
So Thomas, I really have to leave in 5 minutes, okay?
Okay.
I have another appointment.
Then let's say continue another time. I just stop here and then we continue another time.
Well, there's also the possibility that you continue fitting this stuff until you reach the stuff.
I mean, I can try fiddle around with that because right now, like, this is mainly yeah, fiddling with the data, like, till it fits.
So does it mean actually that the PUA and all this stuff there, all this cross-section, back crosstalk and so on, has to be modified, right? So is there a possibility to calculate everything before?
Yes.
Okay.
So
just with the spectra, right?
Just with the spectra and the laser powers.
Okay. Okay.
Because like for the excitations, of course, you need laser powers. Because like this is the prefactor how strong you excite the acceptor. It depends on the spectra and the laser powers.
Okay. Okay. Let me summarize regarding this PDDM parameters. So A to B and B to A are normalized, right? So
A to B, B to A, like this just gives the direction, these numbers. If you have 1, 1, 1, 0, you have thread from A to B. If you have 0, 1, you have thread from B to A. If you have 1, 1, you have thread between A and B.
Okay, but 0, 1 is actually ridiculous, or?
Oh, yeah, then like you have to switch, there's just the names are different.
Okay, okay, so it would be inverted pi, something like this, right?
Yeah, like it's just then A is the acceptor, B is the donor. Like
okay. So PUA could be these are
in this
scalars, right?
What?
So these are it could be also high numbers, right? So any scalar?
Yeah, it could be any scalar. Like internally, it's just multiplied with that number. But I would recommend you to use normalized, so 0 and 1.
Okay. Okay, and the same for the rest. Okay.
Yeah.
Okay, but you would also agree that there's in the red decay, so in the thread sensitized, you can already see that there's some thread, right?
There are some low threads or something.
Okay. Okay, I wouldn't expect just low thread, but
no, like there is something high and something low. Like I would have, I guess, but I would have to play a bit more with the data. So like it's a few minutes to play with that.
Okay, so let me ask one more question. So for high thread, you would expect that there's actually just it's not rounded shaped, right?
Yeah.
That's right. And for low thread, it's super round shaped.
For low thread, it's very round shaped like this. For high thread, it's in principle like should look more like acceptor only.
Oh, okay.
So like for the, it's nice like to have an To have an acceptor that has a short lifetime, because then it's easier to see the differences.
Mm-hmm. Yeah, okay.
But right now, it's like your acceptor has the same lifetime as the donor, and then like low Fred sample is just a bit longer, and high Fred sample is the same shape. So it's
yeah. Okay. Okay. So maybe next time I can serve with a low Fred sample. Okay. That we can yeah, enhance the effect on the Fred sensitized.
Okay, then should we continue another time? Maybe I'll just stop recording now and then
okay,
we discuss.